just to recap, what do we have so far? We realized that this reconstruction problem can be formalized as a linear set of linear equations, where all equations are binary and the variables are binary. We know that there is a sequence of n queries that suffices to reconstruct n rows if there is no noise. Simplest example, the identity, right? Query 1 is what is element 1, query 2 is element 2, etc. We realize that if we add noise, obviously n queries are not necessarily sufficient, but if we increase it a little bit, it would work. And that in exponential time, of course, we can find the solution. But exponential time is not that impressive. So the question is, can we do better? Can we have a polynomial time algorithm that, given a sequence of queries that are rich enough, again, didn't define it formally, let's say a random matrix, and solutions that are guaranteed to be within plus minus alpha of the correct answer, do we have an efficient algorithm for reconstructing with high accuracy the secret binary vector? Any proposals? Sort of hinted in the first slide, but who remembers it?
Well, every time that you ask a query, you're basically saying that you're dividing all the possible vectors of the vector could be into different cosets, you could say, based on how many members of them are true. And the answer will cut off a certain amount of them.
Right. This is basically the visualization we saw before, that gradually we're restricting the regime of possible responses. But optimizing in high dimension in some general polytope is not a very convenient algorithm. But if we, I'm not saying it's impossible, I'm saying it's inconvenient.
It's polynomial.
Polynomial is not necessarily quick enough in typical cases. But there is an algorithm that we're all used to that is really quick, not just polynomial in theory, but in practice, that matches very well linear equations, which is
linear program.
Linear regression. No, linear program is not a quick thing. It's polynomial, but it's not quick in any way. Linear regression, it takes a second. And this looks really like a linear regression. If I would come to you and propose a linear programming technique in a world where you can do linear regression, you won't understand what I want. So before I come and propose linear programming, I need to justify why linear regression is not a good idea. Because think about it. What did I do before? I proposed to optimize over, or to go over, to enumerate effectively all possible solutions and minimize L infinity. But minimizing L infinity is not something we know how to do efficiently. But minimizing L2, we do know how to do efficiently. So a natural proposal is, let's look at it as some binary matrix, some responses that are real. They might be also integers, but I don't care. And we want to minimize this norm. Before it was infinity, let's do it with L2 and call it linear regression. Of course, linear regression would not give us a binary solution, so what can we do? We will project it. How bad can it be? And the answer is, it's typically good until it is not. So now the question is, where can it break? So let's say I had this matrix, had this vector of solutions, I computed this solution, and I got a vector. The vector might be something like, I don't know, 0.3, 0.7, 0.95, 1.3, right? And what would be my guess? Well, the 0.3 I would map to 0, the 0.7 to 1, etc. What were the steps I did formally in order to turn this into a valid solution? I did 2 steps effectively. One is I clipped to be within the range of 0, 1. And 2 is I rounded to be either 0 or 1. And if we want to reason about the accuracy of this process, we need to reason about both effects. What happens, how much does the clipping cost me, and how much does the rounding cost me?
When does the clipping?
If the solution was between 0 and 1, all I did is to round. If the solution was 2.7, then I didn't round, because rounding will give me to 3.
Okay.
I also clipped. So let's see this cool visualization. So the second option is running linear regression. Straightforward. Here's what we do. We have the original vector. We run linear regression. We reconstruct it, and as you can see, there's a relatively low reconstruction error. And of course, it can grow to extremely high data sizes with no problem, right? This took me 0.3 seconds, like literally nothing. Where does it break? So here's a concrete example. Numbers don't matter too much, but like it was chosen to be to result in this specific setting. So this is, you can trust me that there is a specific valid vector B. This is a 3-dimensional regime setting. So B is 1, 0, 0. All responses are within 0.2 out of the correct answer. So that's very small. It shouldn't lead to a problem. Yet, the linear regression would lead to a solution that is outside of the regime in 2 parameters. And as a result, it will round to the incorrect point. So let's try to visualize it. So it was a headache, but here it goes. So it's a 3-dimensional setting. The correct solution is the purple X. Let's start with the left side. Okay? The purple X is the correct solution. And we had a bunch of 3 equations, and there is some feasible regime here.
When is the purple?
So each data...
Oh, where?
Here.
Okay.
The only X that we see.
Uh-huh.
I try to never rely on the colors. I always have also different shapes. Okay? So we have a point. This point corresponds to 1, 0, 0, and this is the correct solution. Okay? And we have those 3 equations, and they create some feasible regime, and that lands. If we optimize using some different method, let's say linear programming, we land somewhere in the area and we round it. Linear regression lands outside of the cube. So now I want to understand its effect. So what I did is I took the slice, the 2-dimensional slice that passes through this solution and the correct solution, and this is what we see here. Okay, so the right side corresponds to a plane in the 3-dimensional regime. The color here is the loss. And what we see is the minima is outside of the valid regime, right? The line that we see here is the edge of the cube. So this is the point 1, 0, 0, and this is the point 1, 1, 0. And this is the correct solution. Problem is, we clip, we get here, and then we round, we get here. Now notice that if we ask which of these two solutions has a better loss, the answer is this one, the correct one. Because the loss landscape points to that solution. But if we do what we proposed, which is find the solution, clip and round, we will land in one with the higher loss. So here's an example where even though this looks like a linear regression, and even though in most cases linear regression will do just fine, it might get us out of the valid regime.
Is it possible to do linear regression while bounding it to the region that we want to be in?
Linear regression, constrained linear regression?
Yeah.
Do we have such a...
Well, none of the values are over 1. None of the values are over
No,
0.
do we have an efficient algorithm for that is as quick as linear regression?
Not quite as... It seems to remember something from mathematical methods. I'm not positive.
If we can always use methods from linear programming, but then we're back to the other solution.
Yeah.
But linear regression, with all of its great attributes that everything is really quick and easy, works when we put no constraints, and when we put no constraints, we might land on an incorrect solution. I'm not sure.
Incorrect?
Sorry?
How much more incorrect?
Arbitrarily, if I work hard enough. Like, I mean, if I manage to get a mistake in only 3 dimensions, that means you can just keep building up and have like a constant fraction with no problem.
The question is, if we're asking random queries, then can the adversary...
No, there's nothing deterministic in the way that the query is boring. The query is just a binary query. The only thing is that we got a response that was basically plus alpha approximately in sum and minus alpha in sum, which is relatively reasonable.
That's the thing. If there exist queries that are problematic...
No, the queries are not special. This is just, and there exists responses that are problematic, but these responses are not even necessarily low probability. And in any case, since we don't want to assume anything about how the responses are produced, we don't want to have attacks that rely on some probabilistic assumption and how the responses are generated. Is everyone comfortable with this example? Because it's like somewhat subtle. Shai? Yeah? Okay. So the problem was that L2 didn't necessarily get us to the right solution, and the clipping caused a serious problem. So what can we do? So now we get to the famous results. First by Nissim and Dino and Nissim, and second by, in a moment we'll see it, by Dwork and Yachnin. So here are the sequence of 3 results that combined tell us that reconstruction attacks are very powerful. Step 1. Again, setting is the setting that we had before. Matrix is binary. Correct unknown variable is binary. And the responses are given within alpha accuracy. If I issue all exponential number of queries, and I found a candidate solution that is alpha accurate, meaning I compare assuming this assignment was correct, then all responses are correct within alpha, then this assignment is 4 alpha accurate, meaning it can't be incorrect in more than 4 alpha coordinates. Alpha is not the fraction, just to be sure, it's the numbers. So it's not between 0 and 1, it's between 0 and n, the number of elements. Right? In other words, if we go back to this visualization, which is up here. It tells me that if I'm in the feasible regime of any point in this regime that is has less than alpha maximal error, has at most 4 alpha error in the Hamin distance. Now, in this example, it's not going to be very impressive. 4 times 1.75 is already 5.5, which is basically already half of the entire signal. But once we start scaling up the sample size, it tells us that up to a constant, the accuracy of your responses tells me what the accuracy of your reconstruction is going to be. Problem is exponential number of queries. So it's not very helpful. So here comes the cool thing. The more impressive result says that even if the number of queries is linear in the sample size, as long as they were just uniform sample, so you don't need to know anything, I don't need to be able to express specific queries, so I don't get into the problem of, oh, I want to construct this particular query, but the API doesn't allow me to create such a query. As long as I can create random queries, and they are alpha accurate, then with high probability, another difference, before it was deterministic, now it's with high probability because it's random, my error will be at most alpha squared. So in particular, if the accuracy of the responses is less than square root of n, then I can reconstruct a constant fraction of the data set.
Does the probability depends on in alpha? In M, of course, it depends, but is it also depends on alpha?
I think no. For any, so you have interplay with all of them. So you can fix the probability, and then you will have here logarithmic dependence on it, or if you want, it won't depend on alpha. It will depend on the relation between alpha and this quantity that we want. So if you want to fix a parameter of the reconstruction error, you want to call it eta, so it will depend on the ratio eta to alpha that you want. Eta to alpha squared. Exponential and eta over alpha squared, I think. I mean, it's easier to think about it the other way around, is eta, the reconstruction error, is proportional to log 1 over beta, the probability, all of that over alpha, times alpha squared. This is the... Okay. So this is the famous result from 2003 that caused people to realize we have a problem. This means that any algorithm that is sufficiently accurate in a way. Now, we might be able to reconstruct data from. Now, you might ask, why didn't this result basically tell us that there's no point in privacy, we're doomed? Like, wherever will be accurate, it won't be private.
More noise.
No, but it seems to suggest that the amount of noise you need to add in order to be private is unreasonable. So it turns out this is not unreasonable, but there's a very narrow path. So what does this tell us, basically? It's that we need to add amount of noise that is at least proportional to square root of n. Right? Less than that, and we can reconstruct the constant fraction of the data. But on the other hand, if we're typical statistical setting, and the data was sampled from some distribution, what is the accuracy we can even hope for in a typical case? Square root of n, right? This is nearly everywhere in statistics this happens. What multiplies the square root of n depends on many settings, on what is the natural randomness of the data, the variance, the covariance, the eigenvalues, whatever. But like square root of n is what we typically get of how does the variance grow if it's a sum, or how does it shrink if it's the average. So it tells us there's a very narrow path. If you add enough noise that is exactly the same scale as the sampling noise, you can still be private. This doesn't break your guarantee, because it says, if alpha is square root of n, then square root of n, then alpha squared is O of n. So if the error is O of n, basically I might have learned nothing. And yet from statistical perspective, what it means is I degraded the accuracy of the algorithm, of the response, with respect to the underlying distribution by at most a constant. But it leaves us a very narrow path. And in a way, the fact that we managed to find a solution in that narrow path and didn't just completely close it and realize there is no solution was not clear at that point, and was a positive surprise. I would mention another work that generalizes it. Pedagogically, it's a nightmare to consider this, but it's important to note that it is that it's true. You might say, you're using the fact that all queries must be within plus minus alpha, and that's somewhat strong requirement which I can easily break. Imagine I add some Gaussian or Laplace noise with variance that is proportional, standard deviation that is proportional to alpha. Then with high probability, most of my errors are within alpha, but with some probability, things go crazy. Maybe that can break the attack. Turns out, no. All I need is that for a strictly larger than half of the responses, the strictly larger than half of the responses were alpha accurate, then it suffices, and we have the same guarantee, just here alpha over eta. So if eta is a constant, let's say 60% were correct, so we just degraded by some constant the result, and we're still in that shape.
When they say alpha eta accurate,
Alpha eta accurate means what it says in the top part, that at least half plus eta fraction of queries got replies that are alpha accurate. So let's say you say 60% were accurate, meaning eta is 0.1. So you plug it in here, and it basically says that 20 alpha squared, which is, okay, it's a big constant, but not crazy. This is what bounds us. So if alpha is small enough constant, let's say 0.1, then let's n times. Sorry?
0.01.
Yeah, I mean, but n times 0.01, or whatever, n over 10. So, sorry, square root over 10. Okay? So let's see it again in reality. Sorry, no. So why does it work? So let's have the visual interpretation and then have the formal claim. So let's look at what we did here. Okay, this was not a very convenient visualization, but let's use this one. So basically, we had a bunch of queries. Each one of them created some small section of the world, and between all of them, we managed to find some small regime that was in the intersection of all three queries. And that was the feasible regime. Right? So, and why did it give us a single solution? Because this regime contained only a single binary point, right? If the possible data sets were arbitrary points within the unit cube, then we have many possible solutions. But since we know it's a binary vector, there was only one solution. So this tells us the following thing. As long as the entire feasible regime is close enough to the corresponding corner, I can try to solve the more general problem of finding an arbitrary point within this range and then just round it. So let's break it piece by piece. Right? This is the point. Let's say I made this query. It gave me some slab within the world. This does not suffice for two reasons. One, there's 4 valid points. Right? And two, as a result, if I round any value here, I won't necessarily get to the correct one. But then I added another one. Okay, now I'm intersecting 2 regimes, so only these 2 are candidates, right? These are not. And then I added another one, let's say, I don't know, this one. This is like a flat one here, and that's it. This is the only one that holds. Now, if the width was too large, then this valid regime, this feasible region, contains points that round to other incorrect Boolean vectors. But if the width is small enough, then the feasible regime here must round to the correct one. So if I only have a way to solve efficiently the problem of finding any point in the unit cube that satisfies all these requirements, I'm done, because then I will round it and everything will be fine. So all I need to do is have a method for finding a point in this area. And the way they do it is they prove that this is indeed, it can be reformulated as a linear programming problem. So, what is a linear program? Let's think of our problem. Our requirement is find a vector, a binary vector, subject to the requirement that some set of equations holds, that some set of inequalities holds, right? This looks like, but is not identical to the problem of integer programming. Integer programming tells us that we need to find a vector that minimizes some inner product with some vector subject to some inequalities. Okay. So first of all, as we said, integer programming is problematic. Integer programming asymptotically effectively is solved in brute force. I mean, there are some better ways, and if you're willing to approximate or have high probabilities, you can do better. But conceptually, it's still a brute force, so we won't get a lot far from it. Okay, so we'll consider linear programming, which is what I said. We're moving to the continuous hypercube. Okay, so now everything is the same. Only difference is the vectors in the linear programming are within Rn, not in the integers, and therefore we will also find a vector that is within the unit cube, and then we will round it. Okay. It still doesn't look the same. Here we only have a requirement. Here we have some optimization problem. So first, we can change the framing of linear programming. This is completely equivalent to restricting x to be within a range. This is the same thing because the inequalities ax is less equal to b and x is greater than 0 means that we can always transform x in some way such that it will be equal to saying x has to be within a certain range. And maximizing and minimizing, of course, is just a matter of the sign. Okay, so this is just renaming the problem in order to have linear programming the way it's typically solved in many packages. And here comes the cool trick. So remember, this is what we had. We were looking for a point within the range. And we knew how to solve the problem of minimizing some target function subject to some constraint.
I'm not sure, why did you add some minimization there? You can minimize like an empty condition, like minimize 0.
No, so this change was only done to match the way the package we're using. This is completely identical. It's rewriting the same conditions in a way that matches the way typical packages use it. That's it. So and it already looks a bit closer to what we're used to. So that's what it will be. But it's meaningless on its own. But here's a big insight. We can add a sequence of extra variables that represent the error pair coordinate. So what do we have here? Here we're saying there is this difference and it needs to be less than alpha. All right? But what we can say is that we have an error and we want to minimize that error. So notice what happened here. Saying that a equation, some absolute value is bounded by alpha, is like expressing that that gap, that absolute error, by some value e, and trying to minimize that e. And of course, we will be able to find one that is less than alpha. So the bottom line is, I can just rewrite, do some algebraic manipulation to the problem of linear programming. Of the reconstruction attack, and rewrite it as a linear programming problem, where what I need is all e have to be between 0 and alpha, and I have these inequalities that basically tell me that the error is bounded by alpha, right, up to some algebra. And now I can solve it with classical linear programming packages. And this is what we have here. So, what we have here is the sequence of what we have here is the sequence of inequalities and the minimizer that I want to have, that result in basically finding the point within the valid regime, the feasible regime, that also has the property that it minimizes the L1 error. So notice, we started with minimizing L infinity. That works, but only in brute force. We moved to L2. That typically works, but doesn't work perfectly in some extreme cases. And now we're minimizing the L1 of the errors under constraints. That is already linear programming. And linear programming we know how to solve efficiently. Now, efficiently is like somewhat stretching things because linear programming doesn't run very quickly. It is polynomial, but polynomial with like somewhat tricky runtime. So you can see we easily get, like even for small numbers, for 100, we already get to tens of seconds. But still, we have here an example of the exact behavior we would expect. So as we increase the noise, here we have a fixed size, fixed number of queries, everything's fixed. You just answer with larger and larger noise. Larger noise effectively corresponds to larger alpha. So we see the reconstruction error grows. Now, I'm not going to get here into the rate. This is not the point of this plot. It just shows us the very general level, the things behave the way we want. And it also shows us that in the typical case, linear regression doesn't work much worse than linear programming. It doesn't, in fact, not worse, but in this case, even slightly better. And linear regression has a slightly lower error, typically. Not a very big difference.
But why?
Why is the error smaller?
Yeah.
I would assume it has to do with the way the noise is generated and the fact that we have a large number of examples. So there's a case to say why it behaves somewhat like a Gaussian from CLT, and therefore minimizing L2 makes more sense, but
It's not a phenomenon.
no, it's not a general phenomena. I mean, in many examples that we considered, linear regression was slightly better. It's easier to find an example where it's slightly better than where it's slightly worse. In order to get it slightly worse, you need to do, or significantly worse actually, you need to be a bit more careful in how you construct your example, but still, you can have them. We have some examples in the assignment. But this is not the main focus. The main focus is that basically both of them work about the same in many cases. So if you want to have something quick to just get a sense, linear regression works. If you want to have something that is formally guaranteed, we can do linear programming. And what we know as a result is that as long as a sufficient number of queries was issued, which is just linear in the sample size, and as long as the error in most of the queries was not too large, no larger than square root of n of the queries, we can hope for privacy. So before we conclude, I just want to end with a very cool example from the last few years that I love, because I think one of the problems with many of privacy's results is that they feel very convoluted and very impractical. Yes, mathematically I proved that you might be able to reconstruct stuff with this attack, but like in the real world, come on. So here's a story from the real world, just I think, 6 years ago. Here's what happened. There's a company called, I don't remember if AirCloak is the name of the company or the system that they created. They claim that they created a method for providing private responses to your queries in a way that is impossible to break. And they didn't use formal privacy guarantees, differential privacy guarantees, but they used a smart idea. What was their idea? They said, look, we will add noise. That's not too much. But what we're worried about is that you will reconstruct the data through these tricky queries. So we'll do the following thing. How do you express the requirement that I want the sum over, a subset of rows? You express it as some, think about a SQL query, which is, the intersection and concatenation between like all sorts of conditions and an or and an and a range and whatever. So they said, okay, the more conditions you add, the more noise I add. So the typical query of a typical user will be, give me the average salary of women in a certain range of ages and, you know, a certain level, education level. Okay, that has like 3 conditions. It's very hard to create very specific attacks, very specific queries with only these 3 conditions. So users that issue this type of queries will pay very small amount of noise. Users that issue very sophisticated queries that are like, yes, and men within that range, or blah, 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 and whatever, will pay more. So the amount of noise scaled somehow with the complexity of your query. They were like, aha, now you can't make any attack against me. Because simple queries don't create sufficiently rich query matrices, and complex attacks, complex queries will result in a lot of noise, enough noise to cross the square root of n, but the utility is not affected because no reasonable no reasonable user would issue this kind of query. Well, so Aloni and Kobi and Nissim from the Dinu Nissim attack, looked at it a little bit. Both have crypto background, and they realized that one of the fields is a random ID, like really random, like has nothing to do with the data. But the query, just to be able to sort of follow up and combine data, allowed you to issue the query also based on like whatever the ID. So they created some condition of like they sampled randomly like 2 primary numbers or something like that, and then the query only depended on the ID in a nice way of like, you know, the ID modulo 1 primary number is like something different one that resulted in the queries being again perfect, near like pseudo random, and they only depended on like the complexity seemed very small, managed to break it completely. Now again, you might say, well, that's because the company was stupid that they allowed this ID and they didn't realize that well, if you give this ID and you allow me to ask the modulo whatever, then I can do whatever I want. That's the point. Whatever you do, as long as it's a heuristic, you always might miss something. You always might forget that, well, someone could do some attack. So, in a sense, this is where we were a year or 2 before differential privacy was created as a notion, and we're now in a way in the state of mind of the people trying to come up with this definition. They're already observing this phenomena that for a very long time we come up with better and better, seemingly better and probably truly better, privacy notions that makes a lot of sense, and then someone realizes, oh, you can break them, and we improve them and you can break them, and we have anonymity, and it's not exactly enough. So okay, so L diversity, so it's not enough. So we had T, I don't remember what it was, close, and it goes on. And then we're like, okay, but maybe iteratively we'll get to the correct definition. And then comes reconstruction attacks and says, no, you need something very general because there's a almost universal attack. So it's exactly 2 options at this point. Either privacy and utility are inherently incompatible, or there's a general method for guaranteeing privacy, ignoring all the details. And in the next lecture, what we would do is try to start from first principles and say, well, we have to be as pessimistic as possible. We will not assume anything, because any assumption about the attacker we realize breaks at some point, and see what can we do starting from there. Okay. Questions? Okay. Thank you.